All right, ready to untangle some seriously fascinating math.
I'm ready. Let's dive in.
Today, we're taking a deep dive into a world where knots don't involve string.
Ah, those tricky mathematical knots, right? The ones you can't untie without cutting them.
Exactly. And to help us on this journey, we're bringing in the power of Lie algebras.
Lie algebras. Those are some seriously abstract concepts. How do they connect to knots?
Well, that's what we're here to find out. We'll be exploring how Lie algebras connect to knot invariants, those mathematical tools that help us distinguish and classify different knots.
I'm intrigued. It's amazing how these seemingly abstract algebraic structures can shed light on the tangled world of knots.
It really is. So, to kick things off, let's unpack one of the fundamental concepts in this area, Vassiliev invariants.
Sounds good. Vassiliev invariants, those are like measuring sticks for the complexity of knots, right?
Exactly. They help us quantify how knotted a knot is, kind of like a spinometer for tangles.
And to visualize these invariants, we use those clever chord diagrams, right?
You got it. Imagine drawing a circle to represent your knot. Then, add lines or chords where the knot crosses over itself.
Each chord representing a double point in the knot.
Right. And the order of those chords around the circle reflects the order in which you encounter them as you travel along the knot.
It's like creating a visual roadmap of those self-intersections.
Precisely. And the beauty of chord diagrams is that they capture not just the presence of those crossings, but also the order in which they occur. That order matters.
Absolutely. But here's a question. Not every arrangement of chords corresponds to a genuine knot, does it?
You're sharp. You're right, there are rules. There are specific rules that determine which chord diagrams are valid, meaning they actually represent possible Vassiliev invariants.
Ah, so there's some underlying structure governing these diagrams. What are those rules?
Well, they take the form of relations that restrict the possible arrangements of chords. One of the simplest is the one-term relation.
What does that one tell us?
It essentially says that a double point in a knot that doesn't interact with any other crossings is meaningless for the overall knottedness.
It's like a lone crossing out in the wilderness. It doesn't affect the overall tangle.
Exactly. The second key relation is the four-term relation. It's a bit more intricate, but it basically establishes relationships between groups of four chord diagrams.
So it's about constraints and dependencies between different chord arrangements.
Right. And these two relations, the one-term and four-term relations, define the structure of what mathematicians call the space of chord diagrams.
The space of chord diagrams. What a cool concept.
It is. It's like a mathematical playground where only those chord arrangements that satisfy those relations are allowed to play.
I like that analogy. So we have this space of chord diagrams, each representing a potential Vassiliev invariant. How do we actually assign values to those diagrams to quantify those invariants?
That's where those weight systems come into play.
Weight systems, those were mentioned earlier. What exactly are they?
Think of a weight system as a function that takes a chord diagram as input and spits out a numerical value or an equation as output.
So they're like translators, converting those visual chord diagrams into something we can calculate.
Precisely. And these weight systems are crucial because they bridge the gap between the visual representation of knots through chord diagrams and the powerful analytical tools of Lie algebras.
Ah, so this is where Lie algebras finally enter the picture. Can you elaborate on how they connect to those weight systems?
Absolutely. But first, let's make sure we're all on the same page about what a Lie algebra is.
Good idea. A refresher never hurts.
Think of a Lie algebra as a set of rules for manipulating abstract objects, like vectors or matrices. It involves operations like addition and a special type of multiplication called the Lie bracket.
So it's a mathematical structure with its own internal logic and rules.
Precisely. Now, when we construct a weight system from a Lie algebra, we're essentially mapping elements of the Lie algebra onto those chord diagrams.
Mapping, meaning assigning specific elements of the Lie algebra to those chords and intersections in the diagram.
Exactly. The way this mapping works gets a bit technical, but essentially different parts of the chord diagram, like the chords themselves, the points where they intersect, and the overall circle, get assigned specific mathematical objects from the Lie algebra.
It's like translating the visual language of chord diagrams into the language of Lie algebras.
Exactly. And the cool thing is that the relations we discussed earlier, those one-term and four-term relations that define valid chord diagrams, naturally get satisfied in this mapping process. It's like those rules are baked into the structure of Lie algebras themselves.
It's elegant how those different pieces fit together. So the end result is a weight system derived from a specific Lie algebra that can analyze those chord diagrams and extract meaningful information about the underlying knots.
Exactly. And this connection between abstract algebra and the seemingly simple world of knots is truly remarkable. Now, how does the Kontsevich integral fit into all of this?
Ah, the Kontsevich integral, that's a big one.
It is. It's a powerful mathematical tool that's considered the universal Vassiliev invariant.
Universal. Does that mean it somehow encompasses all possible Vassiliev invariants?
Got it. It's like a master key that unlocks all those individual invariants.
Wow. How does that work?
Well, the Kontsevich integral is essentially a generating function for all Vassiliev invariants. Think of it as a mathematical recipe that combines chord diagrams and their corresponding invariants in a specific way.
So by manipulating or expanding this integral, you can extract all those individual Vassiliev invariants.
Exactly. That's why it's considered universal. And the beauty is that this Kontsevich integral connects back to those Lie algebra weight systems.
How so?
When you apply a particular Lie algebra weight system to the Kontsevich integral of a knot, you essentially filter the information contained in that integral through the lens of that chosen Lie algebra. It's like specializing that universal invariant to the information that that specific Lie algebra can capture.
It's like looking at the knot through different colored glasses, each pair revealing different aspects of its structure.
Exactly. And this interplay between the Kontsevich integral and those Lie algebra weight systems is a beautiful example of how sophisticated mathematical tools can be used to analyze and understand the seemingly simple world of knots.
Now that we've explored Vassiliev invariants, chord diagrams, weight systems, and the Kontsevich integral, I think it's time to bring in a key player in this deep dive.
Who's that?
Vogel's algebra.
Vogel's algebra.
Okay, I'm ready to learn.
It's denoted by the Greek letter lambda, A, and it introduces a whole new perspective on those Lie algebra weight systems.
Okay, I'm all ears. What makes this algebra so special?
Well, for starters, it's built from those three-legged diagrams, those fixed diagrams as they're called. They're similar to those chord diagrams we discussed, but with a bit more structure.
What kind of structure?
Well, the legs of these diagrams are numbered, unlike the unordered legs of the open Jacobi diagrams. It's a subtle difference, but it has important consequences for how those diagrams interact with the weight systems. I see. So we have these three-legged diagrams as our building blocks. What are the rules that govern how they combine and interact within this algebra?
The defining relations of Vogel's algebra are the AS and IHX relations.
I think I've heard of the AS relation. Doesn't AS stand for antisymmetry?
It does, and it means that if you swap any two legs of a diagram, the result is the negative of the original diagram. The IHX relation, on the other hand, is a bit more intricate, but it essentially captures a relationship between three diagrams that differ only in the way their legs are connected.
So these relations, the AS and IHX relations, impose a certain order and structure on how those three-legged diagrams can interact within the algebra.
Precisely. And the beauty is that these relations mirror certain properties of Lie algebras themselves.
Oh, which properties?
Specifically, the antisymmetry of the Lie bracket and the Jacobi identity. Those are fundamental properties that govern how elements within a Lie algebra behave.
So Vogel's algebra, with its AS and IHX relations, is like a reflection of those key properties of Lie algebras.
Exactly. And this connection goes even deeper. Vogel discovered that those primitive Jacobi diagrams, the ones with a connected internal graph, form a module over his algebra Co.
A module, what does that mean in this context?
It means there's a way to multiply elements of O with those primitive Jacobi diagrams, resulting in new diagrams that inherit properties from both spaces.
So it's a way of combining those diagrams from two different worlds, Vogel's algebra and those primitive Jacobi diagrams.
Precisely. And this multiplication allows us to delve deeper into the structure of weight systems. Vogel found a way to represent certain diagrams within using polynomials in three variables, T and O.
So it's like assigning algebraic symbols to those building blocks of O, those three-legged diagrams.
Exactly. And using these variables, we can manipulate and analyze a wide range of diagrams within as polynomials. The key here is that each of those variables comes with a degree, a number that essentially measures the complexity of the corresponding diagram.
So we're not just dealing with abstract symbols, but also with a way to quantify the complexity of those diagrams they represent.
Precisely. And this notion of degree becomes crucial when we start exploring the connections between Vogel's algebra and those Lie algebra weight systems. Now, remember those characters we discussed earlier, those functions that connect to specific Lie algebras?
Yes, I remember. They act on those elements of at and output numerical values associated with a particular Lie algebra.
Right. And the amazing thing is that Vogel discovered that the characters associated with simple Lie algebras can be expressed using just three numerical values, il, ba, and buck.
Those are the Vogel parameters, right?
Exactly. An ED Lie algebra gets its own unique set of these parameters, like a fingerprint. And what's even more remarkable is that these parameters can be used to express not only those characters, but also other properties of the Lie algebra, like its dimension, the eigenvalues of certain operators, and even the volumes of the corresponding Lie groups.
It's incredible that these three parameters can encode so much information about the structure of those Lie algebras.
It truly is, and this concept, known as Vogel universality, suggests a deeper level of structure underlying these seemingly diverse Lie algebras.
Vogel universality, that's a powerful concept. It suggests that there might be some unifying principle governing the behavior of all those different Lie algebras.
Exactly, and it hints at the possibility of a universal Lie algebra, a sort of blueprint from which all other Lie algebras could be derived. But as of now, its existence remains a tantalizing mystery, a mathematical enigma waiting to be solved.
That's an incredible idea, a universal Lie algebra. I can see why mathematicians are captivated by this possibility.
It really is a fascinating puzzle. Now let's shift gears a bit and dive into the heart of our deep dive, constructing those elusive kernel diagrams for Lie algebra weight systems.
Kernel diagrams, remind me again what those are all about.
They represent those blind spots, those limitations in a weight system's ability to analyze and distinguish certain features of knots. Remember those characters and Vogel parameters we talked about?
Yeah, those parameters that seem to encode so much information about the Lie algebras. How do they relate to these kernel diagrams?
Well, the idea is to find a polynomial expressed in terms of those Vogel parameters that vanishes, becomes zero, when you plug in the specific parameters for a given Lie algebra.
So it's like finding a mathematical key that unlocks a hidden weakness in that algebra's weight system.
Exactly. And for those math-frax now weight systems derived from those special linear Lie algebras, the polynomial that does the trick is iter plus now 2s plus 2s.
It's like a magic formula that zeroes in on a blind spot for those math-frax or weight systems.
Yeah.
But how do we go from a polynomial to an actual diagram?
That's where Vogel's framework comes in. We introduce an element of his algebra denoted as outrain, which essentially represents that vanishing polynomial in diagrammatic form.
So we're translating that abstract polynomial into a specific combination of those three-legged diagrams.
Precisely. And this element will be killed by the math-frax weight system.
Killed. You mean it'll evaluate to zero when acted upon by that weight system?
Exactly. It's like we've found a diagram that the math-frax's weight system simply can't see.
Wow, that's pretty cool. So what do we do with this invisible diagram?
Well, the magic is that we can now multiply this special element by any Jacobi diagram to generate a new diagram that also lies in the kernel of the math-fraxal weight system.
So it's like we're using this element to propagate those blind spots to other diagrams. We're creating a whole family of diagrams that the math-fraxal weight system can't detect.
Exactly. It's a powerful method for systematically constructing those kernel diagrams.
I'm starting to see the implications here. If a weight system can't see certain diagrams, it means it's missing information about the knots those diagrams represent, right?
You're catching on quickly. It means that weight system and any knot invariants derived from it will have limitations in their ability to distinguish certain knots.
So those kernel diagrams are like warning signs, highlighting potential blind spots in our knot analyzing tools.
Precisely. And to make things a bit more concrete, let's look at some specific examples of these kernel diagrams.
Okay, I'm ready for some visuals.
Now, keep in mind that working with those closed Jacobi diagrams can get a bit messy, especially when we're dealing with higher order diagrams with lots of vertices and edges.
Yeah, those can get pretty intricate.
They can. So to simplify things, we often work with those open Jacobi diagrams, the ones with those extra legs.
Right, I remember those. They have that extra grading based on the number of legs they have, which helps organize them.
Exactly. And we can always translate back to those closed diagrams if needed.
It's like choosing the right notation to avoid getting bogged down in unnecessary complexity.
Precisely.
Yeah.
Now, one of the simplest kernel diagrams we can construct is obtained by taking that special element and multiplying it by a simple two-legged diagram. It results in a diagram of order 8, meaning it has 16 of those trivalent vertices.
So we're starting with something simple, a two-legged diagram, and combining it with our blind spot element to create a more complex diagram that the math-frax weight system can't detect.
Exactly. And this order 8 diagram is the first primitive element to appear in the kernel of the mathfrak's null weight system.
Primitive. Does that mean it has some special property?
It does. It means that its internal graph, the part connecting all those vertices, is connected. It can't be broken down into smaller, independent subdiagrams.
So it's a fundamental building block in a sense.
You could say that.
Yeah.
And we can generate a whole family of kernel diagrams by multiplying that special element with various powers of a simple three-legged diagram.
So we're essentially scaling up the complexity of the diagrams by adding more of those three-legged elements.
Exactly. For instance, multiplying by one of those three-legged diagrams gives us a diagram of order 9. Multiplying by two of them gives us an order 10 diagram, and so on.
It's like building a ladder of increasingly complex diagrams, all residing within the kernel of that weight system.
Precisely. And it's not just limited to powers of that three-legged diagram. We can also leverage those marked diagrams introduced by Vogel, especially when dealing with the variable, which corresponds to raising the total marking of a diagram.
Those marked diagrams with their special four-valent vertices and those integer markings, right? How do they fit into the picture?
Well, there are some interesting relations that allow us to multiply diagrams by C under the action of a weight system. It's not a direct multiplication, but rather a manipulation of the diagrams through the lens of that weight system.
So we're exploiting the rules of the weight system to create even more intricate kernel diagrams.
Exactly. And these relations involving those marked diagrams add another layer of complexity and subtlety to the process, but they ultimately expand the range of kernel diagrams we can construct.
This is fascinating stuff. But let's step back for a moment and remind ourselves why these kernel diagrams matter. How do they actually affect our ability to distinguish knots in the real world?
A great question. Remember those colored HOM-FLY polynomials? Those powerful knot invariants derived from the mathfraxal weight systems?
Yeah, we talked about how they can distinguish a wide range of knots.
They are quite powerful. But here's the catch. Those kernel diagrams we've been constructing correspond to Vassiliev invariants that are absent in the colored HOM-FLY polynomials.
Absent. You mean those invariants don't contribute to those polynomials at all?
Precisely. It's as if those polynomials are blind to the specific features of knots captured by those kernel diagrams.
So we could have two knots that appear quite different with distinct structures, yet their colored HOM-FLY polynomials might be identical because those polynomials are simply blind to those differences.
Exactly. It's a humbling reminder that even our most sophisticated tools have limitations. There might be knots out there that look different to our eyes, maybe even have different properties in certain contexts, yet those colored HOM-FLY polynomials can't tell them apart.
It's like those knots have found a way to hide in plain sight.
You could say that. And it underscores the importance of continuing to explore new and more powerful knot invariants, those that can capture a wider range of features, and avoid those blind spots highlighted by those kernel diagrams.
So it's a constant quest for better tools, for a more complete understanding of those intricate knots.
Exactly. The world of knot theory is full of surprises, and those kernel diagrams are guiding us toward a deeper appreciation of the complexities and challenges that lie ahead. Now, shifting gears a bit, let's delve deeper into a specific family of weight systems.
Sounds good. Which ones are we focusing on?
The mathfrak solver weight systems. Remember, those are derived from those special linear Lie algebras we talked about earlier.
Yeah, I remember. They pop up all over math and physics.
They really do. And understanding their limitations is crucial for a wide range of applications.
Okay, so where do those kernel diagrams fit into this?
Well, the researchers behind this work have developed a systematic way to construct those kernel diagrams, specifically for the mathfrak cylinder weight systems.
So we're zeroing in on those blind spots in a very specific context.
Exactly. And their method leverages the power of Vogel's algebra and those marked diagrams, those ones with the extra four-valent vertex and the integer markings.
Right, those marked diagrams. They seem pretty powerful.
They are. And by combining those tools, those researchers have been able to generate a whole collection of kernel diagrams for the mathfrak's NO weight systems, both primitive and non-primitive, up to a certain order.
So it's like a catalog of those blind spots, those diagrams that those weight systems can't see.
Precisely. And they've even proven that those diagrams are linearly independent, meaning they're not just redundant representations of the same blind spot.
So it's a solid, mathematically rigorous collection. But how do these diagrams actually impact our ability to distinguish knots in the real world?
That's the crucial question. Remember those colored HOM-FLY polynomials, those powerful knot invariants?
Yeah, the ones that seem so effective at distinguishing knots.
Well, it turns out that those kernel diagrams can reveal situations where those colored HOMFLOY polynomials fail to distinguish knots that are actually different.
Wait, so those polynomials can be solved?
In a sense, yes. Imagine you have two knots that differ only in the features captured by those Vassiliev invariants that correspond to those kernel diagrams.
So those invariants are the only things that can tell those two knots apart.
Precisely. But because those invariants are absent in those colored HOMFLY polynomials, those polynomials would be completely blind to the difference between those two knots.
So even though the knots are different, those polynomials would see them as identical.
Exactly. It's like those knots have found a way to camouflage themselves, blending into the background as far as those polynomials are concerned.
It's a bit unsettling to realize that even our most sophisticated tools can be deceived.
It is. But it's also exciting because it motivates us to explore even deeper, to seek new and more powerful tools that can overcome those limitations. It's a constant reminder that the world of knot theory is vast and full of surprises.
This deep dive has been amazing. We've explored Vassiliev invariants, unraveled the mysteries of Vogel's algebra, and even touched upon the connections to that mind-boggling Chern-Simons theory.
And we've seen how those seemingly abstract kernel diagrams can have real implications for our understanding of knots and the tools we use to analyze them.
It's a testament to the power of mathematical exploration, revealing hidden connections and pushing the boundaries of human knowledge.
It really is. And to wrap things up, I want to emphasize one key takeaway.
What's that?
The journey of mathematical discovery never ends. There's always more to explore, more to uncover.
So, to everyone listening, we encourage you to keep those mathematical fires burning. Dive deeper into these concepts, ask questions, and who knows, maybe you'll be the one to unlock the next breakthrough in this fascinating field.
Until next time, happy exploring.
Welcome back to the Deep Dive. Ready for another challenge?
Always.
Good, because this one is especially for you math enthusiasts out there.
Oh, this is going to be good.
We're going to untangle the world of knots.
Knots. Like tying my shoes.
Not quite, no. We're diving deep into the math of knots. Think like closed loops in 3D space, and how some really powerful math can be used to, well, reveal some surprising things about them.
I'm intrigued already. What kind of math are we talking about?
Stuff like Lie algebras. But the real kicker is, even with all that firepower, there are knots we still can't fully tell apart.
You're kidding.
Nope. Even with the most advanced tools, some knots just keep their secrets.
Okay, now I'm really hooked. Let's dive in.
All right. I know you're all familiar with concepts like the Jones polynomial and the HOMFLY polynomial.
Second nature.
Perfect. Because we're going to go beyond the basics. We'll explore Vassiliev invariants, Vogel's algebra, and ultimately this idea of a kernel of undetectability.
Sounds intense.
It is, but we'll break it down step by step.
Good, because that kernel thing already has my head spinning a little.
No worries. You're in good hands. We'll untangle it all together.
Yeah.
So let's start with a quick recap. A knot, in math terms, is essentially a closed loop in 3D space, right?
Right.
And the big question is, how can we tell if two knots are truly different? Meaning, can't be deformed into each other without cutting or passing the string through itself.
Ah, the classic problem of knot equivalence. That's where knot invariants come into play.
Exactly. Like mathematical fingerprints. And you already know some of the heavy hitters. Jones polynomial, HOMFOY polynomial, Kaufman polynomial.
Been there, done that, got the t-shirt.
But here's the thing. Even those classics have their limitations, which is what makes this deep dive so cool. We're going to explore these Vassiliev invariants. They give us this way to zoom in on knot differences by looking at versions with tiny crossings, places where the curve intersects itself.
Like taking a high-resolution image of the knot's structure.
Exactly. And to systematically analyze those crossings, we use something called the Vassiliev-Skene relation.
Okay, I'm starting to see how we're getting deeper into those knotty details.
Now, to help us visualize all this, we use chord diagrams. Imagine a circle where each chord represents a crossing in a singular knot.
And the endpoints of the chord show us exactly where the knot crosses itself.
Exactly. But then we go a step further with Jacobi diagrams. Think of them like enhanced chord diagrams with more structure to work with.
More structure means more information about the knot, right?
You got it. An STU relation, a rule that tells us how to transform these diagrams, becomes super important here.
So we've got these visual representations of the knot's information. But how do we actually get numerical invariants from them?
That's where the power of Lie algebras comes in. You familiar with those?
Of course. Generators, structure constants, representations, the whole 9 yards.
Perfect. Because we use Lie algebras to create something called a weight system, which maps a Jacobi diagram to a number. And that number could potentially represent a knot invariant.
So we're using the structure of Lie algebras to extract numerical information about knots. Pretty slick.
Now, get ready for this. There's this elegant mathematical structure called Vogel's algebra. It's denoted by the Greek letter lambda, uppercase lambda. This is going to help us manipulate those diagrams even further.
Oh, I love it when algebra comes to the rescue. What's so special about Vogel's algebra?
One of the coolest things is that certain diagrams, when multiplied by specific elements of lambda, vanish under a weight system.
Wait, they disappear?
It's like finding a secret code that makes parts of the knot's information just, gone.
Now that's what I call a deep dive. I'm ready to uncover those secrets.
All right, so in Vogel's algebra, we use the variables t, sigma, and omega to express elements.
Those are going to be important, I bet.
Oh, you bet they are.
But
They lead us to this mind-blowing discovery. There are knots that look totally different, but all the known Lie algebra-based invariants fail to distinguish them.
no way. Seriously, I thought those invariants were supposed to be like the ultimate knot detectors.
That's what makes this so fascinating. Even the most powerful tools have their limits.
Okay, I'm on the edge of my seat. Tell me more about this Vogel's algebra.
So it's an algebra over the rational numbers generated by these three-legged diagrams.
Three-legged diagrams.
Yeah, think of them as like the basic building blocks of the algebra.
Okay, got it. And we consider them modular the AS and IHX relations.
Right, those relations essentially tell us how we're allowed to manipulate the diagrams without changing their fundamental meaning.
So it's like having a set of rules for playing with these diagrams, ensuring that we don't accidentally change the knot information they represent.
Exactly. And the multiplication in lambda is done by inserting one diagram into a vertex of another.
Like literally plugging one diagram into another.
Yeah, it's pretty visual, actually. But we need to make sure this multiplication is well-defined, meaning it shouldn't matter which vertex we choose to insert into.
That makes sense. Otherwise, we could end up with different results depending on our arbitrary choices. How do we prove that it's well-defined?
We show that diagrams obtained by inserting into different vertices are actually equivalent.
So we're basically showing that no matter which vertex we choose, we end up with the same underlying structure, the same knot information.
Exactly. And that involves applying the generalized IHX relation.
To manipulate the diagrams and show that they're really just different representations of the same thing. Okay, that makes sense.
So once we have this well-defined multiplication, we can really start exploring the structure of Vogel's algebra. We find things like the identity element, denoted by a 1 with a hat on top, and powers of a special element, denoted as x with a hat on top, raised to the power of n.
So we're building up this whole algebraic framework to help us understand knots. But is Vogel's algebra fully understood, or are there still mysteries to uncover?
Vogel made some incredible progress, but there's still a lot we don't know.
Like what?
For instance, we only know the dimensions of lambda up to degree 10. Beyond that, it's still uncharted territory.
Wow, so it's a really complex structure. It makes you wonder what secrets it might be hiding.
Now, we can connect this abstract algebra to something more concrete. Polynomials.
Polynomials. Those are a bit more familiar.
Right. There's this homomorphism, a special kind of mapping, from the polynomial algebra Q-Te-O-Cote to Vogel's algebra.
So we can express certain elements of Vogel's algebra in terms of polynomials.
Exactly. It's like finding a dictionary that translates between these two different mathematical languages.
I like that analogy. Makes it easier to grasp.
And within this dictionary, the variables t, sigma, and omega have specific interpretations in terms of diagrams.
So they're not just abstract symbols, they have a visual meaning. What do they correspond to?
Well, Chinker corresponds to a simple three-legged diagram.
Okay, that makes sense. What about sigma and omega?
Omega corresponds to a more complex combination of diagrams.
So as we go from T to omega, the complexity of the corresponding diagrams increases.
Precisely. But here's the catch. This homomorphism is a projection, a one-to-one correspondence, only up to order 10. Initially, it was thought it might be an isomorphism for all orders, but...
But there's always a but in math, isn't there?
Right. There's always a twist. Turns out, Vogel himself discovered that there are 0 divisors in lambda.
0 divisors, meaning you can multiply two non-zero elements and get 0.
That's it. And that means the homomorphism can't be an isomorphism for all orders.
So there are elements in Vogel's algebra that behave very differently from what we'd expect based on polynomials.
That's the beauty of it. This discovery added a whole new layer of complexity to Vogel's algebra.
I'm sensing that this complexity is going to play a big role when we connect it back to Lie algebras and weight systems.
You're exactly right. But I think this is a good point to pause and let everyone catch their breath. We've covered a lot of ground.
We have. Quick recap, we started with a refresher on knots and invariants, then explored Vassiliev invariants and their visual representations, and finally delved into the intricate world of Vogel's algebra.
And the best is yet to come.
Can't wait to see how all this connects back to the question of distinguishing knots and the surprising limitations we might encounter.
Okay, so we've got this Vogel's algebra, right? How does it actually connect to those Lie algebra weight systems?
That's where characters come in, from group theory.
Yeah, I remember those.
They play a similar role here, but in the context of Vogel's algebra. Essentially, a character tells us how an element of Vogel's algebra interacts with a specific Lie algebra.
Okay. Interaction. I'm trying to picture how all this abstract stuff comes together.
Imagine you've got a Lie algebra, let's call it L, and its associated weight system, denoted Phil L.
Fig L, got it.
This weight system can be applied to diagrams with any number of legs. When you apply Philo to a three-legged diagram, which is an element of Vogel's algebra, what you get is a rank 3 tensor.
And since the structure constant of the Lie algebra is like the only primitive rank 3 tensor we have, it makes sense that the resulting tensor would be proportional to it.
Exactly. And that proportionality factor, that's what we call the character of that Vogel's algebra element. We denote it Chiel.
Chiel. So the character captures how that element of Vogel's algebra behaves when we look at it through the lens of that Lie algebra.
Got it.
So if we multiply a diagram by an element of Vogel's algebra and then apply the Lie algebra's weight system, is it the same as applying the weight system first and then multiplying by the character of that Vogel's algebra element?
Exactly. Captured by the equation filth VL of V hat times fill of U, where V hat is an element of Vogel's algebra and U is any diagram.
Okay, so that equation, that's the link between Vogel's algebra and the Lie algebra weight systems. This is where it gets cool, right? We can use this to build the kernel of a Lie algebra weight system.
The kernel, you mean the set of all diagrams that the weight system maps to 0?
Right, the ones it can't see. So those not features are essentially invisible.
Okay, I see where you're going with this. So if we can find elements of Vogel's algebra that have a character of 0 for a particular Lie algebra, then multiplying any diagram by those elements will make it vanish under that Lie algebra's weight system.
Boom. You got it. We're finding the secret codes that make parts of the knot information disappear.
I told you this was going to be good. So did Vogel figure out how to do that? Find those elements?
He did. For certain series of Lie algebras, like the SLN series, there are specific polynomials in T, sigma, and omega that evaluate to 0 when you plug in the parameters for those algebras.
So if we can express those polynomials as elements of Vogel's algebra, we've found our invisibility cloak for certain knot features. But wait, not all polynomials translate neatly into elements of Vogel's algebra, right?
You're catching on quick.
Yeah.
The ones involving sigma in its pure form, without being multiplied by omega, those are the tricky ones. But Vogel had a workaround.
Oh, what did he do?
He came up with these marked diagrams. They're special linear combinations of diagrams that allow us to handle multiplication by sigma under a Lie algebra weight system, even though we can't represent pure sigma directly in Vogel's algebra. Pretty clever, huh?
That's brilliant. So we've got the tools. Now let's actually build the kernel of a specific Lie algebra weight system. How about the SLN weight system? What does that kernel look like?
For SLN, we have the polynomial PSL. It's alpha plus beta times beta plus gamma times alpha plus gamma, which equals 2t sigma minus omega minus 2t cubed. And that whole thing vanishes when we plug in the SLN Lie algebra parameters. See that sigma term in there?
Ah, so we need those marked diagrams to make this work.
Exactly. The first element of Vogel's algebra that gets killed by the SLN weight system is omega hat PSL. We can express this as 43t t that x hat to the 5th plus 169t that to the 6th minus 83t t that cubed x hat cubed minus 49x hat squared cubed. Or we can visualize it as a combination of diagrams.
So we're generating all these invisible diagrams, but how do we know they're all truly distinct? Could some just be different representations of the same thing?
Great question. We can use a few techniques to check for linear independence. One way is to use open Jacobi diagrams. They have this extra grading based on the number of legs. which makes it easier to see if two diagrams are truly different.
It's like adding another dimension to our analysis.
Another method is to apply a different weight system, one that doesn't vanish on those diagrams. If the values we get are different, we know the diagrams are independent.
And have these techniques shown that the diagrams we're constructing are all distinct?
They have. At least for the first few orders, the diagrams constructed using this method fully generate the kernel of the SLN weight system. We've mapped out its blind spots.
That's incredible. But what about non-primitive diagrams, the ones built by combining simpler diagrams? Do they show up in the SLN kernel too?
They do, but not right away. The first non-primitive diagram in the SLN kernel pops up at order 6. It's a combination of simpler diagrams. Negative open circle, closed circle, negative open circle, times t that squared, negative open circle, closed circle, negative open circle, minus t that, negative open circle, closed circle, negative open circle, times t that, negative open circle, closed circle, negative open circle.
Wow, that's a mouthful. I can kind of see how it might vanish under the SLN weight system, though, since Lie algebra weight systems are multiplicative.
You're right. Applying the SLN weight system to this combination, both terms end up having the same value, but with opposite signs, so they cancel each other out. We can use this principle, and Vogel's algebra, to construct more non-primitive elements in the kernel at higher orders.
So we've got this whole family of diagrams, primitive and non-primitive, that are essentially blind spots for the SLN weight system.
It's like we're mapping out a hidden archipelago in the world of knots. And this leads to some big questions, like, can we always differentiate between knots using these mathematical tools?
Or are there fundamental limits to our understanding?
It seems like our deep dive has uncovered this tantalizing possibility, the existence of undetectable knots. Ready to explore that?
Let's do it.
Okay, so we've been talking about these undetectable knots. Let's get specific. Remember that 8th order diagram we found, the omega hat PSL minus open circle, closed circle, negative open circle? It lives in the kernel of the SLN weight system.
D8. Yeah, that one was a game changer. Really showed us the limits of those invariants.
So we can rewrite D8 as a combination of chord diagrams using that STU relation. And then we can take it even further and translate that into an actual combination of ordinary knots.
It's like those chord diagrams are blueprints telling us how to arrange the crossings in a singular knot. And then we use the Vassiliev-Skene relation to smooth out those crossings and get a combo of regular knots. It's like magic, turning these abstract diagrams into actual knots we can visualize.
Exactly. So we end up with this specific combination of knots, let's call it K8, that corresponds to our original diagram, D8. And because D8 is in the kernel of the SLN weight system, all Vassiliev invariants up to order 8 vanish on K8.
Meaning, if we calculated the colored HOMFLY polynomials for each knot in K8 and combine those polynomials according to the coefficients in K8, all the terms up to order 8 would cancel out. Poof, gone.
It's like this combination of knots becomes invisible to those invariants. They just can't see it.
Yeah, it's a mind-bending consequence of how Vogel's algebra works and how it interacts with those Lie algebra weight systems.
So we've got this invisible knot combination, K8.
Yeah.
But is that the end of the story? Could there be higher order invariants that can see it?
That's the big question, isn't it? It all comes down to whether Vassiliev invariants are complete. If they are, meaning they can distinguish any two different knots, then there has to be some invariant out there that can distinguish K8. But if they're not complete,
then things get really interesting. It means there are fundamental limits to how we can classify and understand knots. There could be whole families of knots out there, hidden from our current methods.
wow. It really makes you appreciate the depth and mystery of mathematics.
Well, we've taken our listeners on quite a journey today. We started with knots, these seemingly simple loops, and went deep into Vogel's algebra, uncovering hidden kernels and the possibility of undetectable objects.
We've seen how powerful these mathematical tools are, but also that even they have their limitations.
It's a reminder that there's always more to discover.
Absolutely.
So to all you math enthusiasts out there, we leave you with a challenge. What new frameworks might we need to crack this knotty problem? What other mysteries are waiting to be unraveled? Keep exploring, keep questioning, and keep diving deep. Until next time. Welcome back, everyone, ready to dive into some serious math. Today we're tackling knot theory and Lie algebras. Specifically, we'll be untangling a research paper about finding the, the kernel of a Lie algebra weight system.
You can think of it like finding the blind spots of a really powerful mathematical tool.
Okay, so we've got this tool that's great at spotting patterns, but there are these shapes it always misses.
Exactly.
Wow, I'm already hooked. And to really see this in action, we'll be using the CELON Lie algebra family, right?
That's right. It's a great example to illustrate these concepts.
Perfect. Now, before we get too deep, let's rewind a bit. Vassiliev knot invariants, I know they're at the heart of this, but remind me, how do they actually work?
So imagine you're trying to measure how knotty a knot is. That's what Vassiliev invariants do. They look at the knot's self-intersections.
Right, the points where the knot crosses over itself.
Exactly. And the really interesting thing is that the value of a Vassiliev invariant depends on the order in which we encounter those intersections as we travel along the knot. This is all captured by the Vassiliev-Skene relation.
So it's not just about how many intersections there are, but the specific sequence of over and under crossings.
Precisely. It's like each knot has its own fingerprint based on those intersections. And to represent this knottiness visually, we use chord diagrams.
Ah, those diagrams with the circle and the lines connecting points, right?
Exactly. Imagine a simple knot with just one self-intersection. We can represent that with a circle for the knot and a single chord across it, the ends of the chord representing those intersection points.
Okay, I see how that works. It captures the essence of the knot's self-intersection. But where do Lie algebras fit into this picture?
That's where weight systems come in. They use information from Lie algebras to weigh these chord diagrams. It's like using different lenses to examine the knot.
So we're using Lie algebras to kind of measure knots.
Yeah. In a sense, yes. We create these weight systems from Lie algebras, and they have to follow certain rules like the one-term and four-term relations.
So the weight systems are constrained by the structure of the Lie algebra itself. That's fascinating. You mentioned Vogel algebra earlier. What exactly is that?
Vogel algebra. It's a framework where we can manipulate diagrams to reveal hidden relationships within Lie algebras. You could say it's a place where diagrams become equations and equations become diagrams.
Okay, that sounds pretty abstract. Could you maybe break that down a little?
Sure. Think of it like this. Vogel algebra is generated by these three-legged diagrams, and they're governed by the AS and IHX relations.
So the AS and IHX relations dictate how we can manipulate these diagrams within the algebra. What do those relations actually look like?
Well, the AS relation basically says if you flip a diagram over a vertical axis, it's considered equivalent to the original. The IHX relation is a bit more complex, involving three diagrams that are only different in a small region.
Got it. So these relations impose a certain symmetry and structure on these diagrams.
Exactly. And within Vogel algebra, we have three key variables, 2, T, and O. They act like building blocks for more complex expressions. They're also associated with what we call marked diagrams.
Interesting. So how do we connect these Vogel algebra diagrams back to specific Lie algebras?
That's where characters come into play. Think of them like functions that map elements of the Vogel algebra to numbers, specific to a given Lie algebra.
So each Lie algebra gets its own set of numbers based on these characters.
Precisely. And to make it even more convenient, we use three parameters, I, wo, and go, to label different Lie algebras. We call these Vogel parameters. They hold a lot of information about those algebras. It's known as Vogel universality.
Okay, so we've got Vogel algebra, characters, and these parameters. How do we actually get to this kernel of a Lie algebra weight system?
The goal is to find those elements in Vogel algebra that, when viewed through the lens of a specific Lie algebra's character, become zero.
So we're searching for elements that essentially become invisible when we look at them through the perspective of a particular Lie algebra.
Exactly. And for the CELON family, there's the special polynomial, CSL plus 2t. It vanishes for all LZLN Lie algebras.
Okay, so this vanishing polynomial is our key to constructing those invisible diagrams. What kind of structures do we actually find inside this kernel? Can you give us some examples?
Let's start with the simplest one, the simplest primitive element. It's denoted by Ushel. This element, when we translate it from Vogel algebra into a chord diagram, reveals a fascinating structure.
Okay, how do we actually go from this element to a chord diagram?
We can use something called the STU relation. It lets us express certain combinations of diagrams in terms of simpler ones.
Like simplifying expression.
Yeah, exactly. And by applying the STU relation, we can transform this primitive element into a specific linear combination of chord diagrams, which we denote as D8.
So now we've got D8, a chord diagram representing an element in the kernel. How does this help us understand the kernel's properties.
Remember, we have that connection between chord diagrams and singular knots. Each chord diagram represents a way a knot can intersect itself.
Right, those self-intersections that give a knot its unique character.
Exactly. So based on D8, we can construct a linear combination of singular knots. Then we apply the Vassiliev-Skene relation to that collection of singular knots.
The Skene relation again, our trusty tool for dealing with those intersections. What happens?
It transforms our collection of singular knots into a linear combination of regular non-singular knots. Let's call this combination K8.
So K8 represents a kind of a knotty embodiment of our invisible diagram D8. Why is this important?
Well, because we started with something from the kernel of the Sulin weight system, all Vassiliev invariants up to the 8th order that are derived from this weight system, they'll vanish when applied to K8.
So K8 is invisible when viewed through the Sulin weight system up to the 8th order.
Precisely. That means if we try to distinguish knots using, say, quantum Sulin invariants, like the colored HOM-FLY polynomials, our K8 would be undetectable up to that 8th order.
It's like K8 has a cloaking device. But how does this relate to comparing two specific knots, like K and K? We've been talking about K8, this combination.
It's a good question. While we've been working with the combination, theoretically, we can manipulate it to isolate the difference between two specific knots.
So like teasing apart the strands of this combination to see the difference between two knots hidden within it.
Exactly. For example, the absolute values of the 2nd order Vassiliev invariant, they're identical for the trefoil knot and the figure 8 knot.
So at the 2nd order, these two knots look the same. Could we use a similar approach to find two knots that are indistinguishable at even higher orders?
Precisely. Extrapolating this, imagine two knots, K and K, that are indistinguishable by all Vassiliev invariants up to the 7th order, but differ at the 8th order by a single unique invariant.
Wow, like almost identical twins, with only a tiny difference that only shows up at a higher level. Incredible. So we found a mathematical blind spot. Knots that seem identical under certain tests, but have this hidden difference revealed by the kernel. What about even higher orders, though? Could there be some higher order Vassiliev invariant or something else that could tell those knots apart?
That's a great question, and it gets to one of the big mysteries. We found this blind spot at the 8th order, but there's no guarantee they stay indistinguishable at higher orders.
So our twins might not be so identical after all, if we keep increasing the magnification. This is really interesting. I'm excited to see what else we uncover as we go deeper.
There's a lot more to explore. In the next part of our dive, we'll get into the implications of this kernel for actually distinguishing between knots that seem identical under other tests.
So we've got these invisible diagrams in the kernel. How do we actually use them to tell knots apart?
Well, remember that link between chord diagrams and singular knots?
Yeah, each diagram represents a way a knot can intersect with itself.
Exactly. Let's take that simplest primitive element, the one we talked about before. We can move that from Vogel algebra into a chord diagram.
Using the STU relation, right?
Yep. It basically lets us swap out certain combinations of diagrams for simpler ones.
Like simplifying an equation.
Exactly. When we use the STU relation on that primitive element, we end up with a specific combination of chord diagrams. We call it DO8.
Oh, okay, so we've got our chord diagram, D8. Now what?
Now we use that connection to singular knots. We can actually build a combination of singular knots based on our DO8.
So we're making a set of knots that, like, embodies the information in the diagram.
Exactly. And then to make things even more interesting, we apply the Vassiliev-Skene relation.
Ah, the Skene relation. What does that do here?
It changes our collection of singular knots into a combination of regular non-singular knots. Let's call this one K8.
Okay, so K8 is like the knot version of our invisible diagram, D8. But how does this help us tell knots apart?
This is the cool part. Because we started with something from the kernel, all those Vassiliev invariants up to the 8th order, the ones derived from the Sicilian weight system, they all disappear when applied to K8.
So K8 is like completely invisible to them up to the 8th order.
Precisely. Which means if you try to distinguish knots using something like colored HOM-FLY polynomials, those quantum Silliman invariants, K8 wouldn't even show up until the 8th order.
So we found a blind spot in those powerful knot invariants.
That's one way to put it. You might be wondering how this helps us compare two specific knots, though, like K and Ka. We've been talking about K8, this combination.
Yeah, good point. How do we bridge that gap?
We've been using a combination, but theoretically we could manipulate it to just focus on the difference between two specific knots.
Like pulling apart the threads of the combination to see the difference between two knots hiding inside.
Exactly. For example, the trefoil and the figure-8 knot, their absolute values for the second-order Vassiliev invariant are identical.
So at that second order, they're basically the same. Could we use something similar to find two knots that are indistinguishable at, like, way higher orders?
Precisely. Imagine two knots, K and KO, that are indistinguishable by any Vassiliev invariant up to the 7th order, but then at the 8th order there's just one single invariant that sets them apart.
Like practically identical twins, except for this one tiny difference that only shows up at a higher level. Amazing. So we've found these knots that seem the same under certain tests, but the kernel reveals this hidden difference between them. But what if we go even higher? Could there be some even higher order invariant or something that could tell them apart after all?
That's the thing. That's a fundamental question. We've found this 8th order blind spot, but there's no guarantee they stay indistinguishable at higher orders.
So our twins might not be so identical after all, if we zoom in even further. This is blowing my mind a little.
It means there's a lot more to investigate. It's entirely possible that a 9th order invariant or even higher could distinguish them.
So our investigation is far from over.
Absolutely. This actually leads to a really big question. Are colored HOMFLY polynomials actually complete knot invariants? Can they, with enough power, actually tell any two different knots apart?
Whoa, that's a big one. What do we know so far?
Well, as far as we know, they could be complete. It might be that colored HOMFLY polynomials and Vassiliev invariants, they're connected in some really deep, subtle way that we need even more powerful tools to understand.
Like we're putting together a huge puzzle and every new piece shows us a bit more of the picture.
Exactly. And this kernel, with its invisible diagrams, it adds a whole other layer to the puzzle. It tells us that even these really powerful tools like colored HOMFLY polynomials, they have limitations, blind spots that could be hiding even more amazing mathematical truths.
This has been quite a journey. We've gone from, what was it, Vassiliev invariants to chord diagrams, then to Lie algebras and Vogel algebra, and now we're even talking about the limits of these powerful knot invariants. What else is there to discover?
There's still more to uncover. In the final part of our dive, we'll switch gears a bit and see how these findings might apply to other areas of mathematics. We'll see how these abstract ideas connect to other fields in some unexpected ways.
Unexpected connections, huh? I'm all ears. How do these invisible diagrams relate to other parts of math?
Well, get this, they actually have links to theoretical physics. Chern-Simons theory, to be specific.
Chern-Simons theory, I've heard the name. But to be honest, I'm not really familiar with it.
It's a quantum field theory. It describes how particles act in 3 dimensions. It's pretty complicated stuff, but basically it uses tools from knot theory and Lie algebras to describe what's happening in physics.
Okay, I see. So where does this kernel of the solenoid system come into play?
Remember how those invisible diagrams just disappear when we use the Chern-Simons system? Well, that disappearing act, it actually affects certain physical quantities in Chern-Simons theory. These things called correlators. They're like mathematical expressions that describe how particles interact.
So you're saying these invisible diagrams are connected to particle interactions in Chern-Simons theory?
Exactly. The really interesting thing is that because of this kernel, certain correlators in Chern-Simons theory with an SUN gauge group, that's a specific kind of symmetry group, they also vanish.
So these physical quantities, these correlators, they become invisible too.
That's right. It means there are certain types of particle interactions that we just can't detect in this specific framework of Chern-Simons theory.
Wow, that's amazing. We went from these abstract mathematical ideas to the behavior of particles in physics.
It really shows you how connected math and physics are. These seemingly abstract concepts can have a real impact on our understanding of the physical world.
This whole journey has been incredible. We started with knottiness and went through Lie algebras, even Vogel algebra, and now we're finding connections to theoretical physics.
Yeah, it's been quite a ride. It shows the power and beauty of mathematics, how even abstract ideas can lead to profound insights.
So to wrap things up, let's retrace our steps. We started with those Vassiliev invariants and chord diagrams, those tools that help us measure and visualize the knottiness of knots. Then we moved on to Lie algebras and their wheat systems, which are like different perspectives on those chord diagrams. And we even took a detour into this abstract world of Vogel algebra, where, diagrams turn into equations and vice versa.
And in that algebra, we found this amazing thing, the kernel of the Spall weight system, a place where those invisible diagrams hide, the ones that vanish when we use the Spall weight system.
Then we looked at how those invisible diagrams can help us tell knots apart, even knots that look identical using other methods. And it highlighted that even the most powerful tools have their limitations, these blind spots that might be hiding even more amazing mathematical truths.
And the best part, we found out these abstract ideas have unexpected connections to the real world. They even influence how particles behave in Chern-Simons theory.
It's been an amazing exploration of how connected math really is, how seemingly different concepts can be linked in ways we never expected. Thank you for joining us on this mathematical adventure. I hope this deep dive has gotten you curious about knot theory, Lie algebras, and the incredible world of mathematics.
Absolutely. Math is always changing, always evolving. There are new discoveries being made all the time. Who knows what other mysteries and wonders are waiting for us to uncover in this vast and beautiful subject.
All right, let's dive into Vassiliev non-invariants. We've got a whole stack of research papers here, full of really intricate diagrams, equations, and even some hints of quantum physics.
Yeah.
I'm really excited to kind of untangle this with you.
Yeah, this is definitely a field where you see abstract algebra, topology, and physics kind of come together in some really surprising ways. But before we get too lost in the math, maybe we should remind ourselves what Vassiliev knot invariants are all about.
Exactly. It's easy to get lost in the details.
Yeah.
So maybe for our listeners who haven't really explored this before, could you give us the elevator pitch for these Vassiliev invariants?
Sure. Think of a knot, just like a tangled loop. And imagine you're trying to classify these knots to tell if two knots are really different or just, fancy versions of the same knot. That's where knot invariants come in. They're kind of like mathematical fingerprints for knots. They assign a value or sometimes a polynomial to each knot, and that can help us distinguish them.
Okay, like how the Jones polynomial really changed how we look at knots.
Exactly. Vassiliev invariants are a specific type of knot invariant, and you can understand them through these interesting diagrams called chord diagrams and Jacobi diagrams. They're almost like a visual language for knots, capturing information about their crossings and tangles.
I love that.
Mm.
They're simple, but they have so much information. And they're connected to quantum physics too, right?
Absolutely. They have deep connections to Chern-Simons theory. That's a quantum field theory that works in 3 dimensions. It's a really cool example of how these abstract math concepts can have implications in physics.
Okay, so we have these Vassiliev invariants. They use these cool diagrams, and they're connected to quantum physics. So this paper we're looking at today asks a specific question. Can you set the stage?
Sure. The question is, do these Vassiliev invariants have all the information needed to tell all knots apart? Or is there kind of a blind spot, a kernel, where they can't tell some knots apart?
The kernel. That's where things get really interesting. And to study this kernel, this paper uses the Vogel algebra, which is written as...
Yeah, the Vogel algebra is kind of like a decoder ring for these Vassiliev invariants. It's built from those Jacobi diagrams we mentioned, and it gives us a way to understand how these invariants work and what their limits are.
I'm ready to dive into that. But first, how are these Vassiliev invariants even defined?
Okay, well, it all starts with something called singular knots. Imagine a knot with places where it intersects itself. Those are singular knots. A Vassiliev invariant of order, say n, is defined in a way that it becomes 0 on any singular knot with more than n of those double points.
So if we have a Vassiliev invariant of order 3 and a singular knot with 4 double points, the invariant is just 0.
Exactly. It's like the invariant can't deal with too many of those intersections. And to show these singular knots and their double points, we use chord diagrams. Each double point on the knot becomes a chord on a circle.
I'm looking at table 1 in this paper, and it's really cool how they show those singular knots as chord diagrams.
Yeah, the nice thing about chord diagrams is that a Vassiliev invariance value on a singular knot not only depends on the order we see those double points as we move along the knot, the chord diagram shows us just that information.
So the chord diagram is like a simplified map showing just those intersection points.
Right. And now we can talk about weight systems. These are functions on those chord diagrams, and they really capture what Vassiliev invariants are about. They're like tools that extract information from the chord diagrams.
Like special decoders for our chord diagram language.
Exactly. And just like language has rules, weight systems have to follow certain relations. There's the one-term relation. It basically means the invariant doesn't care how the knot is sitting in space. It only cares about the knot itself.
So if we twist or turn the knot, the invariant stays focused on its important features.
That's the idea. Then there's the four-term relation. This one is about how weight systems behave when we change the arrangement of the chords in the diagram. You can see examples of this in figures 3, 4, and 5.
Wow, it's amazing that these simple diagrams can tell us so much about complex math.
It is, isn't it?
Mm.
Now, let's move on from chord diagrams to their more complex cousins, Jacobi diagrams. They're similar, also graphs, but they have trivalent vertices. That means points where 3 lines meet. So they're like chord diagrams with more branches.
So Jacobi diagrams give us even more flexibility to describe knots.
Yes. And just like chord diagrams have the four-term relation, Jacobi diagrams have the STU relation. Figure 6 shows this. It helps us simplify Jacobi diagrams and connect them back to chord diagrams.
So we could use the STU relation to go back and forth between these two ways of representing knots.
Exactly. Another cool thing about Jacobi diagrams is that we can multiply them, meaning we can combine them. Figure 8 shows an example. It's like building more complex diagrams from simpler ones.
Like Legos for knots.
I like that. And within all Jacobi diagrams, we have special ones called primitive Jacobi diagrams. These have a connected internal graph. They're really important for understanding how this algebra works.
Okay, so we went from singular knots to chord diagrams, then to Jacobi diagrams, and now to these primitive Jacobi diagrams.
Yeah.
It's like we're zooming in on the core parts of these invariants.
You got it. And now we can finally talk about the Vogel algebra. It's a special algebra that's built from these three-legged diagrams, and it also uses the AS and IHX relations.
So this algebra comes from these diagrams, the rules they have to follow. What's interesting is that primitive Jacobi diagrams of order 2 or higher become a module over this Vogel algebra, right?
Right. That means we can use A to study and work with these primitive diagrams. It gives us a powerful tool to understand knot invariants.
So A is like a control panel for these diagrams, helping us see how they work.
I like that way of putting it. One of the most important findings here is that there's a special mapping called a homomorphism from a polynomial algebra to A. This brings in variables called A and O, and we can use them to adjust and study the elements of A.
So we're connecting polynomial expressions to this algebra of diagrams. Equation 3.1 and figure 14 show how we can write diagrams using polynomials. It's like translating between visuals and symbols.
Exactly. And through these variables, saltint, Dirac, and Wood, we start to see how complex all is, its size, what it does at higher orders, and even the fact that it has 0 divisors.
0 divisors. What do those mean in this case?
They mean you can multiply two things in that aren't 0, and the answer is 0. Sounds strange, but it shows how complex this algebra is.
It feels like we're just beginning to understand what I can tell us about knot invariants. But before we go deeper into that, let's talk about Lie algebras. They seem to be pretty important here.
Definitely. Lie algebras are those structures you learn about in linear algebra, and they actually create weight systems on Jacobi diagrams. It's a really cool connection showing how different parts of math are linked.
Wow, so we're linking linear algebra to these abstract diagrams. It's like math is coming full circle.
Exactly. We call the character of something an S, col. It's a number that connects the weight system of that element to something called the structure constant of a Lie algebra L. Basically, it tells us how much a specific Lie algebra is influencing the weight system linked to an element in S.
We're using the character to see how much Lie algebra flavor something in SML has.
That's a great way to put it. Every Lie algebra has its own parameters. We call them TL, OL, and SL. They define the Lie algebra's personality.
Just like people have different personalities, Lie algebras have different parameters. And this leads us to something called Vogel universality, right?
Yes, not just characters, but other things about Lie algebras, like their dimensions, the dimensions of their representations, even volumes of Lie groups, can be written using parameters called S and S. These come from those characteristic parameters. Equation 3.3 and Table 2 show this really well.
So we found a kind of code that links different properties of Lie algebras. It's like finding a mathematical Rosetta Stone.
Definitely a cool connection. And it leads to the idea of a universal Lie algebra. It's a hypothetical thing that might hold all this universality, but we haven't found it yet.
A universal Lie algebra sounds like the holy grail of this field. But for now, let's get back to the main point, the kernel of the weight system. Specifically for Cn, the special linear Lie algebra.
Right. The kernel. That's the set of elements that the weight system turns into zero. It's like that blind spot we talked about before.
Yeah, the place where the weight system can't tell things apart. Table 3 shows some estimates of the kernel's size. And to build things that are part of this kernel, we use a polynomial called CSL. This polynomial becomes 0 for Cn.
Exactly. CSL is like a key to this kernel, specifically for CL.
And when we put in the specific values of Iwa and Fobro for CLN, the polynomial magically becomes 0.
Exactly. Like a lock and key, the CLN values are the lock. If the key fits, the lock opens, and that means the polynomial becomes 0.
Very elegant. But how do we actually use this polynomial to make things that are part of the kernel?
Well, there are a few tricks. One way is to take a primitive Jacobi diagram, remember those with the connected internal graph, and multiply it by a special element of A that uses our polynomial, phi SO. For instance, a cell is basically phi SL written in language of Phi. We can use this to make diagrams that are in the kernel.
Okay, I see in figure 16, post-cell is expressed using those XXN diagrams we talked about. It's really cool how we can visualize these abstract ideas.
Isn't it? Table 4 shows us a bunch of diagrams that are in the kernel of the cell weight system. They all come from multiplying primitive Jacobi diagrams by the right elements of A, using phi SL.
So we take those primitive diagrams, add some phi SL, and boom, we have things in the kernel.
Exactly. Those diagrams in Table 4 are actually called open Jacobi diagrams. They have another way of being organized based on the number of legs they have. This makes it easier to check if they are linearly independent.
So open Jacobi diagrams make calculations and checks for linear independence easier.
That's right. To make sure they're really independent, we can use a different weight system, like the sun weight system. If it gives us different values for each diagram, then we know they're truly unique.
We're using sun to double check, making sure those kernel elements are really different.
Exactly. Now, when we compare the number of these kernel diagrams we made with the estimates in Table 3, something really cool happens. The diagrams we made actually generate the entire kernel of Alron for those primitive Jacobi diagrams up to order 10.
It's like we've mapped out a big chunk of this mathematical blind spot.
We have. And things get even more interesting when we look at non-primitive diagrams. Those are Jacobi diagrams made by multiplying simpler diagrams.
Like using Legos to build the bigger structures.
Precisely. Table 3 shows that these non-primitive diagrams first show up in the kernel of the Sloan weight system at order 6.
So at lower orders, it's all primitive diagrams.
Yeah.
But as we go higher, we start seeing those non-primitive diagrams.
Exactly. And our source material tells us that the reason these non-primitive diagrams show up in the kernel is because of how Lie algebra weight systems work with multiplication.
Well, what do you mean by that?
Well, if you have two Jacobi diagrams, let's call them D sub 1 sub and D sub 2 sub, and you want to find the weight system of their product, L D sub 1, D sub 2 sub, you just multiply their individual weight systems, L D sub 1 sub, L D sub 2 sub. The weight system respects the multiplication.
It's like the distributive property for weight systems.
Exactly. And this is important for understanding why some non-primitive diagrams end up in the kernel. Look at figure 18. It shows a non-primitive diagram in the 6th order kernel. We can actually write it as a combination of products of simpler diagrams.
So we're breaking that complex diagram down into simpler ones.
Exactly. Because of that multiplication property, the weight system for this whole thing becomes simpler. When we apply L to the U, we get LELC, which simplifies to do sub soup.
So we're using the fact that the weight system of a product is the product of the weight systems.
Precisely. The same thing happens with the other term, too. Its weight system also simplifies to suplevel subdis. Since both terms simplify to the same thing, their difference, which is our original non-primitive diagram, becomes 0 under the weight system.
Ah, I see. They cancel each other out, putting that non-primitive diagram in the kernel.
Exactly. We can use this trick, breaking down non-primitive diagrams into products and using that multiplication property to make other things that are in the kernel at higher orders. Figures 19 and 20 show more examples.
So we're building this collection of kernel diagrams, and we're figuring out why they belong there and how they're connected. But how does all this relate to the physics of Chern-Simons theory? We mentioned earlier how not invariants can come from the Wilson loop in this theory.
Right. What's amazing is that the kernel actually affects what we can see physically. If a diagram is in the kernel, it means that certain correlators, those are physical quantities that we can measure, can't be found from the Wilson loop.
So because of the kernel, there are limits to what we can learn about not physics from the Wilson loop in Chern-Simons theory.
That seems to be the case. For a Lie algebra like Serie N, the kernel tells us about relationships between the group factors in the Wilson loop. These are terms that involve traces of Lie algebra generators. These relationships mean some correlators are hidden.
So it's like the kernel creates a blind spot in our observations.
You could say that. What's really interesting is that for the SUN gauge group, which is linked to something called the colored HOMFLY polynomials, one of these primitive correlators is already gone at the 8th order. It's hidden in the kernel, so we can't see it directly from the Wilson loop.
So there's a limit to what we can learn about not physics from the Wilson loop, at least for some gauge groups.
Based on what we know now, that seems to be true. It's amazing how this mathematical kernel is linked to what we can observe in physics.
Definitely. But now I'm wondering, if some Vassiliev invariants can't tell certain knots apart because they're part of the kernel, does that mean those knots are truly the same? Are there knots that look different but have the same fingerprint, even though they're not actually the same?
That's a really good question. To look into this, we can start with the simplest element in the kernel, the primitive one, d sub 8 sub from figure 16.
Okay, let's take a closer look at that.
Right.
Okay, so we're using this d sub 8 sub diagram to maybe find knots that the Sullen weight system can't tell apart.
Right. We can use this diagram along with something called the STU relation and the Vassiliev-Skene relation to try and make a combination of knots that might have the same values for the Sullen weight system. It's like looking for knots that have the same fingerprints, even if they look different.
So it's kind of like we're working backwards. We start with something in the kernel and then try to find knots that might be indistinguishable.
Yeah, exactly. First, we use the STU relation to rewrite d sub 8 sub using chord diagrams. This gives us a specific combination of those chord diagrams. We'll call it d sub 8 sub. It's like we're translating from the language of Jacobi diagrams to the language of chord diagrams.
And then we can use those chord diagrams to think about singular knots, right?
Exactly. Each chord diagram represents a specific type of singular knot. So we can use d sub 8 sub to build a combination of singular knots.
So we're going from a diagram to a bunch of those singular knots, the ones with those self-intersections.
Right. The last step is to use the Vassiliev-Skene relation on these singular knots. This lets us get rid of those self-intersections, and we end up with a combination of regular knots not without those intersections. We'll call this combination k sub 8 sub.
So we started with d sub 8 sub, which is a diagram in the kernel, and now we have k sub 8 sub, which is a combination of regular knots. What's so special about k sub 8 sub?
Here's the thing. Because d sub 8 sub was in the kernel of the SOAN weight system, all those Vassiliev invariants that come from that weight system up to order 8 will be 0 when we apply them to k sub 8 sub.
0. You mean all those invariants will give us 0 for this particular combination of knots?
Yep. Those invariants can't see k sub 8 sub, and since the colored HOMFLY polynomials are made from those SIM Vassiliev invariants, k sub 8 sub won't be distinguishable by those polynomials up to the 8th order.
So we've basically found a bunch of knots that are invisible to the colored HOMFLY polynomials up to a certain point. It's like they're hiding in plain sight.
That's a great way to think about it. Now the question is, can we take this further? Can we use k sub 8 sub to find two specific knots, let's say k and k, that the Sullen weight system can't tell apart?
That's the big question, right? If we could find that, it would really show the limits of these invariants, at least for some Lie algebras.
Definitely. We don't have a surefire way to do this, but we can play around with the math a bit. Remember, from one chord diagram, we can make tons of singular knots. We can combine these singular knots, adding and subtracting them with different numbers in front, hoping to find a combination that simplifies to just the difference of two regular knots, kk.
So we're kind of like rearranging these singular knots, trying to make them show us a simple difference between two regular knots. Sounds like a puzzle.
Exactly. For lower order diagrams, we can do this manually. For example, at the second order, we know that the absolute value of the second order Vassiliev invariant is the same for the trefoil knot and the figure 8 knot.
So there are already knots that share the same value for at least one Vassiliev invariant.
Yes, and this hints that maybe there are knots that share even more invariants. It's possible that we could find two knots that look the same to all Vassiliev invariants up to, say, order 7, but then differ at order 8.
Wow, that would mean they're basically invisible to all those colored HOMFLY polynomials up to order 8.
That's right. But here's the important thing. Even if two knots have the same Vassiliev invariants up to a certain order, they might not have all the same invariants. Maybe higher order invariants or even completely different kinds of invariants could tell those knots apart.
So this kernel is important. but it doesn't necessarily mean we've hit a wall in our ability to distinguish knots.
Hmm.
Maybe there are other mathematical tools out there that can help us see these subtle differences.
Exactly. This research gives us more questions than answers. It's a challenge to explore new math and think about different kinds of invariants to really understand knots.
It's exciting and kind of humbling to realize how much we still don't know. Before we finish up, I want to go back to the connection with Chern-Simons theory. We talked about how the kernel affects what we can actually observe physically, creating a kind of blind spot in how we understand not physics. Could you explain that a bit more?
Sure. Remember how in Chern-Simons theory we can calculate physical quantities called correlators using the Wilson loop? These correlators tell us about how particles interact in this quantum field theory.
And the kernel of the solenoid system tells us that we can't access some of those correlators.
Exactly. Because of the kernel, there are relationships between certain terms in the Wilson loop. These relationships basically hide some of the correlators from us. It's like they become invisible when we try to calculate them the usual way.
So the kernel is like a filter, blocking some of the information in the Wilson loop. Does that mean we're missing important information about the physics of knots?
That's a question that researchers are still working on. It's possible that those hidden correlators have important physical information that we just haven't figured out how to get to yet.
So we've hit a bit of a roadblock in understanding Chern-Simons theory using the Wilson loop. Are there other ways we might get around this kernel limitation?
That's a hot topic in research right now. Some physicists are looking at different things in Chern-Simons theory, things besides the Wilson loop, to see if they can find those hidden correlators.
It's like we're searching for new ways to see into this quantum world, trying to find a different angle that will show us those hidden parts.
That's a great way to put it. It's an ongoing challenge to develop new tools, both in math and physics, that can help us unlock the secrets of Chern-Simons theory and how it connects to knot theory.
This deep dive has really taken us through a lot. From simple knots to complex diagrams to abstract algebra and even quantum physics, we've seen some pretty amazing things about the limits of Vassiliev invariants and how they relate to knot physics.
And we've only just scratched the surface. This kernel finding shows just how deep the connections are between different areas of math and physics. It's really quite surprising.
Okay, before we get too lost in all this, let's take a minute to recap the main points from this exploration. I think it would be helpful for our listeners to process all this.
Sure, that's a good idea. Let's start by going back to the idea of a Vassiliev knot invariant. Remember, it's a function that gives a knot a value, and that value becomes 0 when we apply it to a singular knot that has more double points than the invariance order.
Right, it's like the invariant has a limit on how much knottedness it can handle. And we saw how these singular knots, the ones with the self-intersections, can be represented by these elegant chord diagrams.
Exactly. Those chord diagrams capture the important information about the self-intersections, and they're the building blocks for understanding Vassiliev invariants.
And then we moved on to weight systems. Those are functions defined on those chord diagrams, right? They're like the mathematical tools that help us extract meaning from those diagrams.
Precisely. Think of weight systems as the bridge between the visuals of those chord diagrams and the more abstract world of algebraic invariants. They give us a way to translate visual patterns into specific mathematical values.
And those weight systems aren't just random functions. They have to follow specific rules, like the one-term relation and the four-term relation, which make sure these invariants work properly and capture the essential features of knots.
Right. Those relations are super important because they guarantee that our invariants are consistent and don't get messed up by superficial things about how we draw or represent the knots.
And then we went even further, generalizing those chord diagrams to Jacobi diagrams, which introduce more complexity with those trivial vertices, the points where three lines come together.
Exactly. Jacobi diagrams give us a richer language to describe knots, and they have this really cool connection to Lie algebras, which are these fundamental structures in linear algebra.
And that link to Lie algebras is where Vogel universality comes into play. This universality shows us a hidden structure that many different Lie algebras share, and it lets us describe many of their properties using just a few parameters.
It's a truly amazing result. It points to a deep unity in the world of Lie algebras, which seems so diverse on the surface, and it hints at the possibility of a universal Lie algebra that might include all of this shared structure.
It's like finding a universal language that lets us communicate across different mathematical worlds.
Perfect analogy. But the real focus of this deep dive was the kernel of the Solon weight system. This kernel is basically the set of all things that the weight system associated with the special linear Lie algebra, SAN, maps to 0.
Right, and the paper we've been discussing provided a clever way to construct elements of this kernel, using that special polynomial, VSL, and the power of the Vogel algebra.
Exactly. Using those tools, we were able to create a collection of diagrams that belong to this kernel. And these diagrams point to potential limitations in the ability of Selin-based Vassiliev invariants to distinguish all knots.
It's like finding a blind spot in our mathematical vision. And this blind spot has consequences not just for knot theory, but also for how we understand the physical world through the lens of Chern-Simons theory.
Definitely. The existence of this kernel tells us that certain physical quantities, those correlators we talked about, are hidden from us when we try to calculate them using the Wilson loop in Chern-Simons theory.
It's as if the kernel is creating a shadow, blocking some of the information that we could potentially get from this quantum field theory.
A very poetic way of putting it. And this discovery creates exciting new avenues for research. It challenges us to find new ways to explore Chern-Simons theory and to develop new mathematical tools that might help us get around this limitation that the kernel imposes.
So, even though this deep dive has highlighted some limitations in what we currently know, it has also ignited a curiosity and a desire to learn more.
Absolutely. And that's the beautiful thing about scientific inquiry. Every answer we find often leads to even more intriguing questions, leading us further into the unknown.
And sometimes, exploring the unknown leads to unexpected connections and hidden treasures. We started with simple knots and ended up exploring complex diagrams, abstract algebras, and even the quantum realm. Along the way, we saw how interconnected all of these areas of math and physics truly are.
It's really quite amazing. Studying knots demonstrates the power of human curiosity and the endless possibilities for discovery in the mathematical universe.
I love that. Well, on that inspiring note, it's probably time to wrap up this deep dive. I hope our listeners have enjoyed this wild ride through the world of knots. I encourage everyone to keep exploring the vast and fascinating world of mathematics.
Until next time, happy knotting.
So, as we wrap up this deep dive into Vassiliev knot invariants, what are some of the key things we've learned? What should our listeners really take away from this?
Well, I think one of the biggest takeaways is that even in a field as seemingly well-established as knot theory, there are still surprises waiting to be discovered.
Yeah, like this kernel business, right? It's almost like we hit a wall, a limit in our ability to tell some knots apart using these particular mathematical tools.
Exactly. And that's the beauty of research, isn't it? We push the boundaries of what we know, and sometimes we encounter these unexpected roadblocks. But those roadblocks often lead us to new and exciting paths of inquiry.
So this kernel discovery is less about a dead end and more about opening up new possibilities.
Precisely. It challenges us to think outside the box, to consider alternative approaches, and maybe even develop entirely new mathematical tools to overcome these limitations.
I like that perspective. So where do we go from here? What are some of the big open questions or future directions in this area?
Well, one obvious direction is to try and find ways to see those knots that are currently hidden in the kernel. Maybe there are other types of Vassiliev invariants, or perhaps entirely different kinds of knot invariants that can distinguish those knots that the Sill weight system can't.
It's like we need to develop a new kind of lens, a different way of looking at knots that can reveal those hidden features.
Exactly. And that might involve delving deeper into the connections between knot theory and other areas of mathematics, like representation theory or even category theory.
It sounds like there's a lot of exciting work ahead.
Absolutely. And this research also has implications for physics. Remember that connection to Chern-Simons theory? The kernel of the Sill weight system suggests that we might be missing some crucial information about the physics of knots.
Yeah, that's right. Some of those physical quantities, the correlators, are inaccessible because of this kernel. It's like they're hiding in a shadow. So how do physicists plan to address that?
Well, some are exploring different ways to approach Chern-Simons theory beyond the standard techniques using the Wilson loop. They're looking for new observables, new ways to probe the theory, hoping to uncover those hidden correlators.
It's a fascinating challenge. They're basically trying to find a new window into this quantum world, a different perspective that might reveal those hidden aspects of the theory.
Precisely. And that's what makes this field so dynamic and exciting. There's this constant interplay between mathematics and physics, each discipline enriching the other and pushing the boundaries of our understanding.
This deep dive has really been a journey. We've gone from the basics of knots and Vassiliev invariants to the complexities of the Vogel algebra, and even touched upon the mysteries of quantum physics.
And we've only scratched the surface. But that's the beauty of it, isn't it? There's always more to explore, more to learn, and more connections to be made.
Well, on that note, I think it's time to wrap up this deep dive. I want to thank you for guiding us through this fascinating world of knots and for sharing your insights.
It's been my pleasure. I always enjoy talking about knots.
And to our listeners, I hope you've enjoyed this exploration as much as we have. Keep those minds curious and never stop untangling those knots of knowledge. Welcome back, deep divers. Today, we're going to be knotting things up a bit.
Oh,
We're diving into knot theory and Lie algebras.
okay.
And our main source is this research paper exploring how to construct the kernel of a Lie algebra weight system,
Interesting.
like finding a mathematical sieve to isolate specific knot properties,
Right.
with implications even for quantum field theory.
Yeah, what's really intriguing about this paper is how they use Vogel's algebra.
Oh,
This diagrammatic tool that really helps reveal the hidden structures connecting knots and Lie algebras.
I love how this research brings seemingly abstract math into practical applications.
Yeah.
So let's get started.
Okay.
So the paper starts by talking about Vassiliev invariants, which act like fingerprints for knots,
Uh-huh.
allowing us to distinguish them from each other.
That's right. And these invariants are particularly interesting when applied to singular knots.
Singular knots.
Yeah, so these are knots that intersect themselves at double points.
So it's like identifying a person based on their scars or like distinguishing features.
Exactly. And the paper even mentions chord diagrams as visual representations of these double points, essentially mapping out the knots' crossings.
Okay.
And Table 1 in the paper actually shows us examples of these singular knots and their corresponding chord diagrams.
Whether we can actually visualize this.
Exactly. It's a helpful visual aid.
Okay, cool. Now let's move on to weight systems.
Yeah.
These are functions that operate on chord diagrams
Right.
to extract valuable information about the knot.
Exactly. But these functions aren't arbitrary.
Okay.
A valid weight system has to satisfy specific rules, namely the one-term and four-term relations, which act as checks to ensure mathematical consistency.
So it's like having a quality control system for our mathematical tools,
Yeah,
ensuring they're reliable and accurate.
precisely.
Okay. The paper then briefly mentions the Vassiliev-Kontsevich theorem,
Yeah.
which establishes a powerful connection between weight systems and Vassiliev invariants.
Well, this theorem is crucial because it suggests that understanding weight systems can give us deep insights into Vassiliev invariants and vice versa.
So it's like saying if you know the fingerprint, you can understand the person.
Precisely.
Wow, that's a powerful connection.
It is.
Now, the paper introduces a new type of diagram, the Jacobi diagram.
Okay.
Can you explain what those are?
Think of Jacobi diagrams as an extension of chord diagrams.
Okay.
They include trivalent vertices,
Trivalent vertices.
which are points where three lines meet, and a special cycle called the Wilson loop.
Interesting. Do these diagrams have any special properties or operations?
Yeah, they have a unique multiplication operation,
Right.
allowing us to combine and form more complex structures. And we use AS and IHX relations to manipulate and simplify these structures.
Okay, so we've got Vassiliev invariants,
Uh-huh.
chord diagrams, weight systems, and now Jacobi diagrams, all playing a part in understanding knots.
It's all coming together.
Yeah, it's all connected, but
Yeah.
how do Lie algebras fit into all of this?
That's where things get really interesting.
Go.
Lie algebras, which represent symmetries in mathematics,
Right.
can be used to create weight systems called Lie algebra weight systems.
Okay.
These systems map parts of a Jacobi diagram to elements within the Lie algebra.
Okay, so we're starting to see connections between these seemingly disparate concepts.
Exactly.
The paper then delves into Vogel's algebra, denoted as algebra.
Right.
Can you explain what that is and why it's relevant?
Vogel's algebra is a special algebra constructed from three-legged diagrams with specific rules.
Okay.
It's a powerful tool for understanding the structure of Lie algebras and their weight systems.
And how do we represent elements in this algebra?
We use special variables,
Okay.
t,
Okay.
sigma, and omega,
Yeah.
that encode information about the algebra's structure. Think of them as the building blocks of this mathematical language.
Okay.
And figure 14 in the paper shows some visual representations of elements in highlighting their intricate structure.
So we can see how they fit together.
Yes.
It's like deciphering a new code.
It is.
Now, the paper mentions something called characters on Vogel's algebra.
Right.
What are those and how do they relate to Lie algebras?
Each Lie algebra has a unique character that acts as a function on elements of a dais.
Okay.
These characters are parameterized using three numbers: alpha, beta, and gamma,
Gamma.
which capture the unique properties of each Lie algebra.
So it's like each Lie algebra has its own personality reflected in these parameters.
Precisely.
I see that Table 2 lists different Lie algebras and their corresponding Vogel parameters.
Yeah.
Almost like a cheat sheet.
Exactly. This table is a helpful reference for understanding the relationships between different Lie algebras and their characters.
Now, the paper discusses the construction of the kernel of a specific Lie algebra weight system, specifically SLN.
Right.
Can you explain what the kernel is and why it's important?
The kernel in this context consists of specific Jacobi diagrams that are effectively nullified.
Nullified.
Yeah, like they're made to equal 0 by the weight system,
Okay, so they disappear.
essentially.
That's intriguing.
Yeah.
Does the paper give us any visual examples of these diagrams in the kernel?
Yes. Table 4 shows some diagrams from the kernel of SLN, giving us a concrete visual representation.
Okay, so we've explored Vassiliev invariants, chord diagrams, wheat systems, Jacobi diagrams, Lie algebras, and Vogel's algebra.
It's a lot.
I know it's a lot to take in, right? All interconnected in this fascinating web of mathematical concepts.
It is fascinating how it all connects.
Yeah, but what does this all lead to? What are the practical implications of this research?
That's what we'll be exploring next.
Okay.
The paper connects this kernel construction to Chern-Simons theory,
Chern-Simons theory.
a tool physicists use to describe certain quantum phenomena.
Okay, so we're starting to see how this seemingly abstract mathematical exploration can have implications for understanding the physical world.
Precisely. And the existence of this kernel also has significant implications for knot detection, specifically for our ability to distinguish knots using quantum invariants like colored HOMFLY polynomials.
This is getting really interesting.
It is.
I'm eager to learn more about these implications and how they connect to the bigger picture of knot theory and quantum field theory.
Let's delve into that further.
Okay.
The paper goes on to explain how the kernel can actually mask subtle differences between certain knots, making them indistinguishable by some of our most powerful mathematical tools.
So it's like realizing that our current methods of knot detection might have limitations, and there might be knots out there that we can't yet differentiate.
Exactly. And this raises some profound questions about the completeness of our current knot invariants and whether there are knots that even the most sophisticated mathematical tools can't tell apart.
So even our most complex math might not be enough
It might not be.
to fully grasp the subtleties of these knots. This opens up a whole new avenue of exploration, pushing the boundaries of our understanding of these seemingly simple yet incredibly intricate mathematical objects.
It really highlights the depth of knot theory.
It does, and the beauty of it.
Absolutely.
So this is where it gets really interesting.
It does.
Because now we're going to find out if our tools are good enough.
Yeah. Are they up to the task?
Or if there's more that we need to discover.
Let's find out. Welcome back to our deep dive into the world of knots and Lie algebras. Before we move on, I want to highlight a fascinating possibility the paper explores. We've seen how a combination of knots K8 can be constructed to be indistinguishable by Vassiliev invariants up to the 8th order.
Yeah, it's like they're wearing identical masks, at least from a certain perspective. Could we take this further and manipulate these mathematical knots to transform that combination into a difference between just two knots?
The paper suggests this is theoretically possible, though there's no set algorithm. It would involve experimenting with various combinations of singular knots, adding and subtracting them, to see if we can isolate a difference between two distinct knots.
I imagine it like trying to disentangle a messy knot. You keep trying different moves, hoping to find the magic sequence that leads to a clean separation.
That's a great analogy. And for lower order invariants, this manipulation might even be achievable manually. The paper gives an example using the second order Vassiliev invariant. It turns out the absolute values of this invariant are the same for the trefoil knot, denoted 31, and the figure 8 knot, denoted 41.
So even though these knots appear quite different visually, they share a specific mathematical property, at least at the second order.
Precisely. This hints at the possibility that more complex knots might share even more properties, making them indistinguishable by a whole range of lower order invariants.
Let's say we have two knots that are identical according to all Vassiliev invariants up to the 7th order, only differing at the 8th order. Would those be incredibly difficult to tell apart?
Absolutely. Even colored HOMFLY polynomials, which are based on these invariants, wouldn't be able to distinguish them up to the eighth order of their perturbative expansion.
That's mind-boggling. It's like two objects casting the same shadow from almost every angle, making you wonder if they're truly different or just cleverly disguised. But what about higher-order invariants? Could they potentially differentiate these seemingly identical knots?
That's a crucial question. The paper argues that there's no inherent reason why higher-order Vassiliev invariants couldn't distinguish such knots.
So maybe these higher-order invariants contain more subtle information about the knot structure, information that's not captured by lower-order invariants, like looking at a fingerprint under a microscope, revealing intricate details we wouldn't see otherwise.
Exactly. So even though we can construct combinations of knots that appear indistinguishable up to a certain order, higher-order invariants, or even entirely new invariants, might hold the key to unveiling their hidden differences.
This brings us to a fundamental question about the completeness of knot invariants. Are colored HOMFLY polynomials, as powerful as they are, truly complete in their ability to distinguish all knots? Or could there be knots out there that are so subtly different that we need a whole new level of mathematical sophistication to tell them apart?
That's a fascinating open question in knot theory. The paper suggests that both colored HMFLY polynomials and Vassiliev invariants could potentially be complete knot invariants. In principle, they might contain all the information needed to distinguish any two knots, no matter how similar they appear.
It's almost like saying that no two fingerprints are truly identical, even if it takes incredibly advanced technology to detect those minute variations.
Yes, but the relationship between these invariants might be incredibly complex and interwoven. We might need to unravel layers upon layers of mathematical structure to fully grasp how they capture those subtle nuances of knot topology.
This highlights the beauty and challenge of knot theory. It seems like such a simple concept, yet it leads to these incredibly deep and complex mathematical problems.
Absolutely. And it's a testament to the power of mathematical tools to help us understand the world around us, even at the most fundamental levels.
Speaking of powerful tools, let's shift gears slightly and revisit Vogel's algebra, denoted as no situation. We touched upon it earlier, but I'm eager to delve deeper into its structure and significance.
That's a great suggestion. The paper emphasizes that Vogel's algebra is still largely unexplored territory. For instance, its dimensions are only known up to the 10th degree, which speaks to its complexity and the ongoing research surrounding it.
It's like we're exploring a vast, intricate cave system where every turn reveals new and unexpected formations. There's a sense of mystery and wonder, with the promise of hidden chambers and undiscovered beauty yet to be found.
I love that analogy. And despite its complexity, mathematicians have made significant progress in understanding Vogel's algebra. For example, there's a homomorphism, a specific type of mathematical mapping, from the polynomial algebra QT plus S to O to Vogel's algebra.
So it's like building a bridge between two different mathematical landscapes, allowing us to translate concepts and insights between them.
Precisely. And this homomorphism is incredibly useful for representing elements within Vogel's algebra. We can express elements of OB using polynomials in the variables tan, Potcast, and O.
It's fascinating how these seemingly simple polynomials can encode the intricate structure of diagrams within Vogel's algebra. Does the paper provide any specific examples of this?
Yes. Equation 3.1 showcases how these polynomials can represent elements of Vogel's algebra, demonstrating their expressive power. But there's a fascinating twist. It turns out this homomorphism is not an isomorphism, meaning it's not a one-to-one mapping. Vogel discovered that there's an element denoted pedo of order 15 in Vogel's algebra that when multiplied by the element results in 0. This implies that Vogel's algebra contains 0 divisors, elements that can multiply with other elements to produce 0.
That's a surprising and intriguing property. It's like finding a secret passage within the cave system that leads back to the starting point, challenging our understanding of its layout.
Exactly. And this discovery highlights the ongoing exploration and research surrounding Vogel's algebra. It's a rich and complex mathematical object with the potential to unlock even deeper insights into the relationship between knots, Lie algebras, and quantum field theory.
This has been another fascinating leg of our journey. We've discussed the possibility of manipulating combinations of knots, the potential limitations of even our most powerful knot invariants, and the complexities of Vogel's algebra.
Indeed. We've even touched upon the concept of a universal Lie algebra, a hypothetical object that might generalize Lie algebras and encompass even broader mathematical structures.
It sounds like there's still so much to uncover and understand in this realm of mathematics. I'm eager to see where our deep dive takes us next.
Welcome back to our deep dive. We've been exploring this intricate world of knots,
Uh-huh.
Lie algebras, and Vogel's algebra. In this final part, I'm excited to see how these concepts come together to unlock
Right.
deeper insights into knot theory and quantum field theory.
Let's pick up where we left off with the fascinating concept of characters on Vogel's algebra.
Okay. Remember, each Lie algebra possesses a unique character
Right.
which acts as a function on the elements of algebra.
It's as if each Lie algebra has its own personality,
Precisely.
its own unique way of interacting with the elements of this algebra.
And what's truly remarkable is that these characters can be parameterized using three numbers: alpha, beta, and gamma,
Okay.
known as Vogel parameters.
So these parameters capture the essence of each Lie algebra.
Exactly.
It's like their unique fingerprint in this vast landscape of mathematics.
Precisely. And the paper provides a handy reference, Table 2, which lists various Lie algebras and their corresponding Vogel parameters.
It's almost like a cheat sheet.
Exactly. It's a valuable tool
Yeah.
for navigating this complex algebraic world. Now, remember those weight systems we discussed earlier?
Yes.
They can be extended to operate on fixed diagrams with any number of legs, as long as they satisfy the AS and IHX relations.
So it's like expanding the capabilities of our mathematical toolbox, allowing us to handle even more complex and intricate diagrams.
For simplicity, let's denote this generalized weight system for a Lie algebra L as AL.
Okay.
This weight system maps a fixed diagram with n legs to a rank n tensor,
Okay.
obtained by contracting the structure constants of the Lie algebra.
So it's a way of translating the structure of the diagram
Yes.
into the language of tensors,
Exactly.
capturing its essential properties in a more compact form.
To illustrate this, consider the diagram shown in Figure 15.
Okay.
Applying the weight system L to this diagram
Uh-huh.
gives us a rank 4 tensor,
Okay.
L sup sub CD sub,
Supo sub speetel.
which represents an endomorphism on the tensor product L2.
Okay, so we're seeing how the diagram transforms into a dynamic mathematical object
Yes.
that operates on a specific algebraic space.
Now, when we apply the weight system L to an element Vogel's algebra,
Okay.
we obtain a rank 3 tensor, and due to the unique properties of Lie algebras, this tensor must be proportional to the structure constant F of the Lie algebra.
It's fascinating how we're uncovering these hidden connections,
Yes.
these fundamental relationships between the structure of Vogel's algebra and the core elements of Lie algebras.
This proportionality coefficient in this relationship is called the character of the element VU. This character is crucial for understanding how Lie algebra weight systems interact with elements of Vogel's algebra.
So by understanding these characters,
Yes.
we can gain a deeper understanding of the relationship between these different algebraic structures.
Exactly. The authors delve into the specifics of calculating these characters for elements of Vogel's algebra.
Okay.
Of the form two
They introduce a convenient parameterization using three numbers,
Okay.
TL, UL, and TEL,
TL, OL, and so.
which depend on the Lie algebra L and the normalization of the metric tensor.
So they're essentially simplifying the process of calculating these characters.
By expressing them in terms of these parameters.
And it makes the underlying structure more transparent. They then go on to present a more elegant parameterization. Using the Vogel parameters, Istas and Go.
Right, alpha, beta, and gamma.
These parameters are related to T, Sus, and O
Okay.
through a set of equations, equation 3.3,
Equation 3.3.
providing a more unified and insightful way to express characters and other Lie algebra properties.
It's like finding a common language.
Yes.
A universal framework for describing the diverse properties of Lie algebras.
Precisely, and this leads to a truly remarkable concept: Vogel universality.
Vogel universality.
It turns out that not only the characters on Vogel's algebra, but also other properties of Lie algebras, such as dimensions, eigenvalues of Casimir operators,
Okay.
and volumes of Lie groups can be expressed as functions of these Vogel parameters.
That's incredible.
It is.
It suggests a hidden order, a unifying principle connecting seemingly disparate aspects of Lie algebra theory.
The authors offer a specific example in equation 3.4,
Equation 3.4.
showing how the dimension of a Lie algebra can be elegantly expressed in terms of Vogel parameters.
It's beautiful how this framework weaves together this intricate tapestry of Lie algebra theory, revealing the interconnectedness of this mathematical world.
However, the paper acknowledges that while Vogel universality has illuminated many aspects of Lie algebra theory,
Okay.
it primarily focuses on the adjoint sector,
The sector.
involving tensor powers of the adjoint representation.
It seems we've explored a significant portion of this mathematical landscape,
Yes.
but there are still uncharted territories waiting to be discovered.
Indeed. The authors even mention the intriguing concept of a universal Lie algebra, a hypothetical object that could potentially generalize Lie algebras
Okay.
and encompass even broader mathematical structures.
That's a tantalizing thought.
It is.
It seems our deep dive has revealed not only a wealth of knowledge,
Right.
but also a whole new set of questions and avenues for exploration.
You're absolutely right. It underscores the ever-evolving nature of mathematics.
And the endless pursuit of deeper understanding.
Exactly.
This deep dive has been a fascinating journey
It has.
through the intertwined worlds of Knott's Lie algebras and Vogel's algebra.
Absolutely.
We've seen how these seemingly abstract concepts have profound implications
Right.
for understanding the physical world, from the classification of knots to the behavior of quantum fields,
We've explored intricate diagrams, uncovered hidden relationships.
and witnessed the power of mathematical tools to help us unravel the mysteries of our universe.
And as always, the deep dive continues.
It does.
There are still countless mysteries to unravel, connections to discover, and insights to be gained.
So keep exploring, keep questioning, and keep diving deep into this fascinating world of mathematics.
Absolutely.
Who knows what wonders await you in the depths of this boundless ocean of knowledge?
I'm sure there are many.
Until next time, stay curious.